is the chat? All right, perfect. So one thing that I am really bad at is seeing chat messages. So if you guys write a message in the chat and I keep going on and I don't acknowledge it, please just turn on your mics and let me know that there's something in the chat so I can respond to you guys. All right. So Civi 665 Introduction to the Finite Element Method. As you guys know, I believe that this is a prerequisite for civil students, but of course we have more than just civil students with us today. I know that we have a couple mechanical engineers as well as a couple chemical engineers, so it's really exciting, quite a broad background of students. Now, for the instructors of the session, there's going to be me, Clayton. You guys can just call me Clayton. And I will be the ones that you guys basically interact with. So when it comes to assignments, when it comes to lectures, anything like that, I'm your guy. You come talk to me. But we also have a second co-instructor, Dr. Samar Adib. He does more of the background stuff, just ensuring the quality of the course, stuff like that. So as you guys may or may not know, Samar is the guy who would run this course in the past. It's my first time teaching it, so a little bit nervous, but I think we can have a lot of fun with this course. So if you guys have any questions, my email is right here. Please feel free to email me about anything you guys need, whether it be questions about the lectures, question about the assignment, or the final project, stuff like that. I'm always happy to help. So just message me whenever you guys like. All right. So when we get into this course, there's actually a lot to talk about. As you guys are going to see, the finite element method is such a broad course. And even by the end of this particular course, you guys will barely be just scratching the surface. We're going to talk about the topics when we get to eClass, so I'm not going to cover those right now, but there's a lot to cover in this course, but it's going to be a lot of fun. Now, the thing that you guys are probably very interested in is the marking scheme for this class. So there's actually going to be three components. The first one are assignments. As you guys are going to see, there's going to be 9 assignments and they are going to be due weekly. Now, luckily for you guys, there is no assignment associated with this first lecture. As you guys are going to see, this first lecture is kind of boring. It's just some mathematical preliminaries that we need to know before moving on. So there's going to be a total of 9 assignments, and they're going to be worth 35% of your guys' final grade. Now, the second thing that we have is a final project, which is going to be due at the end of the term. It's going to be worth 30%, and we're going to talk about that a little bit later. Now, the project, even though I'll get into more specifics later, it's a very open-ended project. Basically, what the project's going to be is you guys can use any finite element software of your choice and solve a problem of your choice. So if you guys are doing research, and let's say you guys are, for instance, doing a steel beam or the buckling of a steel beam, that would be a very good project for this class. You can show how you guys can use the finite element method and a finite element program to solve that particular problem. So the final project, we'll talk again a little bit later, but it should be a nice fun way to introduce yourselves to finite element programs and show that you guys can solve problems using finite element programs. Now, the last thing that we have, of course, is going to be a final exam. It's going to be worth 35%, and it will be due near the end of the term. I have right now end of the term. This will probably change. It'll be due before the end of the term, and it's going to be a take-home exam. So there's going to be no crazy stringent time limits, anything like that. What I'll probably do is I'll release it and give you guys maybe 2, 3, maybe even 4 days to complete it. And of course, there will be a submission box for that. So should be a nice relaxed class. That's what I'm hoping for. Anyways, I know you guys probably have a lot of stress with your other classes, perhaps your research, stuff like that. This should not be adding to that stress. This should just be a nice, fun time. Textbooks. So Dr. Samar Deeb, who's the co-instructor of this course, as you guys know, he made a very detailed online textbook, which is great. So as you guys are going to see in eClass, whenever I'm talking about a specific section, I'm going to reference this online textbook. So if you guys want a little bit more information, you guys can go to the online textbook, and it shows you guys proofs for stuff like that. It's a very nice resource and completely free, so you guys don't have to pay anything out of pocket, which is great. Now, some of you guys may say, you know what, Clayton, I prefer a more in-depth guide, lots of examples, stuff like that. And if you guys want some additional text and references, Dr. Samar has listed a couple down here. So basically just pick your poison. There's a bunch to pick from. The one at the bottom from Klaus Spath right here, he's actually the finite element, kind of the founder. Not the founder, as then he invented it, but he pioneered a lot of it. And he was actually from the University of Calgary back in the day. He did his master's in Calgary and then did his PhD at Berkeley, and he's been the finite element instructor at MIT for the past like 40 some years. So this is a good book, but it's a little bit more on the advanced side. So if you guys want a lot of good info, that's your guy right there. Course website, again, this is going to be the online textbook website. You don't really need to worry too much about the link because when I show you guys in eClass, I'll actually provide the links to each section of the textbook, so it should be nice and easy to see. After that, we basically just have a bunch of university policies. In essence, don't cheat. Please don't cheat. No cheating, no plagiarism. Everything will be just fine. You shouldn't have to worry too much about this course. When it comes to assignments, I'm going to provide you guys with lots of examples, stuff like that. So everything should be straightforward. There should be no need to stress over trying to find a solution to something. I should be able to help you out. And then, of course, the learning outcomes for this course, there's going to be lots, but in essence, we want you guys to be able to implement that finite element method in the analysis of the mechanical response of structures and components. So I know that there's a lot of mechanical engineers out there, a lot of chemical engineers. You guys may say, oh, I'm not too concerned about structures. The good part is it doesn't really matter. Once you guys figure out the finite element for something like steel, you guys can apply it to whatever you guys want. So I'm not too sure what you mechanical or chemical engineers do, but there will be a way to implement the finite element method into whatever you guys are doing. Now, this is kind of going to be the breakdown of our actual stuff. And what I'm going to do is I'm going to go to eClass for that because actually I'll go here and then I'll go to eClass. So as you guys are going to see, there's going to be 10 lectures in total. We have an 11th lecture down here, which I put to be determined because the course really ends at lecture 10. Now, when it comes to the final exam, stuff like that, we're only going to be worried about lectures 1 through 10, and I'm going to use lecture 11 as kind of a bonus lecture. And what I'd like to do actually is ask you guys what you guys would like to know about the finite element method. As I kind of suggested before, we're really just scratching the surface with what we cover here. There are so many different models and implications of the finite element method that, of course, some stuff is going to be left out. So if you guys have something in mind, like let's say XFEM, which has to do with crack propagation, stuff like that, you guys say, hey, Clayton, I want to learn a little bit about that, and perhaps we can squeeze it into lecture 11. Now, when I say that we're only scratching the surface, that's not to say that by the end of this course, you guys will not know what the finite element method is. By the end of this course, you guys will definitely know what the finite element is, what the basics are, how it's implemented, stuff like that. But if you look at, say, lecture 8, where we're talking about material plasticity models, we're going to be covering steel as well as concrete. Now, of course, there's a lot more materials than just steel and concrete, and that's why I say we're just scratching the surface. We're picking very common materials, but of course, if you're dealing with something like aluminum, per se, that won't be covered here, and that'll be something you guys will need to do on your own. So the whole class should be done by the end of the term, which is April 16th, I believe, the Friday, and that's when your final project is due. Now, the final exam will be done before the final project, and what I'm thinking right now, tentatively, so of course this can change depending on what you guys have to say, but I'm thinking of having the final exam on Monday, April 5th, so not the Easter, but during that week. That's my goal for right now, but of course, you guys have other classes, you guys have other commitments, so if that doesn't work, I'm sure we can work out something together to make it nice and easy for all of us. So that, in essence, is the syllabus. Is there any questions about the grade breakdown, anything like that before we move on, or are you guys feeling pretty confident so far? Hopefully. You guys can respond in chat. If you guys don't say anything, I'll assume it's good. Otherwise, I feel like I'm just talking to myself. All right, I'm not seeing anything so far, so if you guys have any questions, just let me know. Now we're going to move on to eClass. So this is eClass, and what I did is I split it up into sections. So again, we're going to have 10 lectures. That's going to, it's going to be basically the course in itself, lectures 1 through 10. Now, as I said, we only have 9 assignments. So again, lecture 1 here, this linear algebra review, that's not going to have an associated assignment. Assignments 1 through 9 are going to be based on lectures 2 all the way down to lecture 10. So I have an assignment tab right here. I have the first 3 assignments posted. You guys can complete them. And what I would like you guys to do is once you guys complete the assignments, you can scan them, or if you guys do them in the Word document, they'll already be there. But basically just combine your assignment into one single PDF, and I have submission boxes for each one of the assignments. So if I click on assignment 1 over here, we can see that it is due on Monday, the 25th of January. So you guys still have 14 days. And again, assignment 1 is going to be based on lecture 2 right here, the solid mechanics lecture. All right, so that's going to be the assignment. Final project, again, I haven't really defined it yet. We're going to talk about this more perhaps next week. But again, it's going to be an open-ended project, so nothing nothing to worry about too much here. And you guys still have lots of time. So this final project is going to be due at the last day of classes, which is Friday, the 16th of April. So you guys still have just over 3 months to complete it. And I will also be posting sample projects that other students have completed, so you guys won't be in the completely in the dark when you guys get to the final project. And of course, we have the final exam, which I will release to you guys, give you guys, let's say, 4 or 5 days to do it, maybe less, maybe more, depending on what you guys want. And you guys can just complete it, submit it, it should be good to go. So in terms of things that you have to submit for marks, it should be a nice, easy class that way. I know with online delivery, it could be really, really hard to write an exam in 3 hours or something like that. So don't worry about that. I'll give you plenty of time for the final exam. There should be no stressing in this course whatsoever. So the next thing I want to talk about really quick is just programs that we are going to be using in this course. So if you guys have taken solid mechanics with Dr. Sammer, you guys are probably familiar that we use Mathematica a lot. So Mathematica is a coding-based program. It basically makes a lot of math that we do in this course very, very simple. So Mathematica is something that I highly recommend for your guys' assignments. Now, for your guys' assignments, I'm not saying that you guys need Mathematica. If you guys choose, let's say, MATLAB to solve the problem, or even Python, that's completely fine. You guys can use whatever you want. I just personally recommend Mathematica, and when I'm doing my own personal examples on showing you guys how to solve these particular things, what I'm going to do is do it in Mathematica. So Mathematica might give you an edge because if you guys see me do it, it might be easier for you guys to implement rather than in MATLAB where all the commands are a little bit different. So it makes it a little bit more challenging. So Mathematica is the first one. Again, it's recommended, but it's not required. The program that is going to be required is Abacus down here. So down here we have some installation guides for Abacus. It's completely free if we're using the if we're using the student version, which you guys should be. And Abacus will be a part of both your guys' assignments, especially when we get to the second half of the course, as well as your final project. So the final project, I said you guys can use any finite element program you guys see fit. So if you guys are, let's say, mechanical engineers and you guys really love ANSYS or something like that, you guys can use ANSYS. I don't really care, as long as you guys are using a finite element program. But the finite element program that we're going to be discussing in detail in this course is going to be Abacus. So what's going to happen is when we see like lecture 4, 5, and 6, I'm going to show you guys how to implement these things in Abacus. So once you guys get to the final project, you guys will actually be very well implemented in Abacus. So hopefully it'll make your guys' lives a little bit easier. So again, we have the download links here. Just follow the instructions. It's fairly easy, but I'm sure that a lot of you guys have already used Abacus if you guys are doing research. It's kind of the research finite element program of choice because it has so many different capabilities. It's not just limited to structures or something like that. It can basically do anything you want it to do, provided you know what you're doing, of course. All right, so last thing I'm going to just run down really quick is just the lectures. So of course today it should be a nice easy lecture, pretty boring lecture if I'm being honest with you guys. Linear algebra is never extremely fun, but it is important in this class. So the lecture today, I'm just going to go through an introduction of the course, and then we're just going to do a brief linear algebra review. So we're going to start off with linear vector spaces, and then we're going to move on to matrices, which you guys will see me also call tensors a lot. So you guys are MN students, MSc students, and PhD students. I expect that you guys already probably know matrices, stuff like that. So again, should be a nice, easy lecture for you guys. Now, when we get to the rest of the lectures, most of them are pretty easy. except for lecture number 2. So lecture number 2 is again another review lecture, and it is solid mechanics. So solid mechanics is a listed prerequisite of this course. However, I know that a lot of you have not taken solid mechanics. When I took this course back in the day, I didn't take solid mechanics either. So it's actually not too bad that if you guys don't know solid mechanics, don't worry. We're basically going to cover the entire course in one lecture. Now we're going to keep it fairly simple because we don't need to know too much about solid mechanics, but this will be a heavier lecture just because there is a lot to cover after solid mechanics. So again, lectures 1 and 2, linear algebra and solid mechanics, it's basically just going to be review. It's going to be a good time. But at the end of solid mechanics here, especially Euler-Bernoulli beams, this, of course, will be assignment number 1. So I just got a question asking if I'm recording my lectures. Yes, I am. So I'm recording the lecture right now. I'm going to post it to YouTube. And down here under recorded lectures, this is where I'll be posting the links. So after the lecture's done, I'm going to upload it. And then I'll put the link here saying lecture 1, blah, 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 blah. So you guys can access the entire lecture whenever you guys want. Now, another thing I'm going to be doing, which I haven't done yet, as you guys have probably seen, is I'm going to create lecture videos for each specific topic. For instance, if I'm looking at lecture 1 here and I forget a little bit of linear algebra review part 1, I don't want to have to go to that 3-hour recorded lecture and try and figure out what I want. So what I'm going to do is I'm going to create little mini videos in each one of these. So for instance, I'm going to create a video just covering the linear algebra review part 1 posted here. So if you guys are just concerned about that particular part, you guys will see it here. I didn't have access to my recording equipment during the vacation, which is why no videos have been posted yet. But don't worry, the videos will be posted later today. So each one here will have a video. And if there's examples of that particular topic, I will also put the example videos in there as well. So there'll be a lot of videos to cover. You guys don't have to worry. I'll make sure that everything is very accessible to you guys. All right. So again, lectures 1 and 2, it's going to be a review. And then after that, we're going to actually start getting into the finite element method. How do we calculate it? What exactly do we do? Stuff like that. So it should actually be a lot of fun. I'm personally excited. I'm not too sure if you guys are excited, but I personally am. It should be a nice, fun course. All right, guys. So, yeah. Let's get started. Do you guys have any questions before we get started? Anything on your guys' mind? Any concerns for this course? Again, I'm hoping that this will be a nice, easy course for everybody. Have a great time. Perfect. So we're going to start the presentation now. Slideshow, current slide. All right. So again, this first lecture, I'm just going to apologize to you guys. It's going to be boring. Linear algebra review is not really fun for anybody. Well, it's fun for the nerds, of course, but for most people that like applicability, it's not the best. But it's nice to show that there is applicability to the course. When I first took linear algebra, it was a nightmare because I thought like infinite vector spaces, like what does this mean? I had no idea. However, as we're going to see in the finite element method here, it actually does serve a purpose, which is surprising, but also very useful, and it's I find it quite nice after this. Now, don't worry. If you guys have taken linear algebra and you guys think, oh, that math's really complex, we're going to keep it quite simple. The nice thing for us is we live in a 3D world. So therefore, we don't need 4D, 5D, or 6D vector spaces. As you guys are going to see, everything is going to be simplified into 3D. At most complexity, we could even do things in 2D. But before we get into that, we're just going to do a little introduction into the course. So let's begin. What is finite element analysis? Now, this is a very, very open-ended question. There's a lot of different answers you guys can give, but we're going to start off with a simple example. So let's take this right here. Let's take a problem where we say that we have x squared is equal to 2. Now, just looking at this, we say, you know what? Well, that's pretty easy, Clayton. It's easy to see that the solution, of course, is going to be x is equal to the square root of 2, right? So that's actually not too bad. But what would the finite element version be? How can we approximate this? This is what we're going to get into, is approximations. So let's say instead of just looking at this and knowing the solution, we were to plot it. So what I can do is I can take my function f of x, which is equal to x squared minus 2. So I just took that 2, moved it to the other side and plotted it. And I can tell that there is going to be a root there at the square root of 2. So it's pretty easy to see this. But how do I implement this in a computer program, or how can I approximate this? Well, the key here is that our function f here is a nice continuous function. Therefore, we can perform a Taylor series expansion. So of course, f of x, oh, this should be f of x plus h. Already a mistake, sorry guys. I just fixed this really quick. The introduction slide was the hardest. So this should be f of x plus h is equal to that, plus the partial derivative of f of x with respect to x multiplied by h plus 1 over 2 to the explanation mark, blah, 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 blah. Now, we can neglect higher order terms. We don't need the second derivative of f of x. We can keep it nice and simple. So we can say f of x plus h is equal to f of x plus the derivative of f of x multiplied by h. Now, luckily for us, we know that all of this is equal to 0, because again, we're looking for those roots. So what we can do is we can take this equation, make it equal to 0, and we can solve for h. Now, when I put all this here, I know it's really confusing to look at. You say, Clayton, what exactly did you just write? I'm a little confused. Well, it's basically this. What we can do to get to this root is we can do an approximation. We can pick an x naught, or an initial guess of what that root is going to be. And then with this equation, we can do this. We can find out what the value of that function is at our initial guess. We can find the slope of the tangent line, and then we can enter this point over here. So the distance between x naught and over there is a magnitude of h. Therefore, we have a new guess of x naught plus h. So this is a little bit confusing. Let's go into an actual example. So if we look at our particular problem, we know that f of x is equal to x squared minus 2. We also know that f prime of x, which is just simply the derivative, is going to be 2x. So the first step when we do these approximations, we're always going to need to assume an initial value. So in this case, let's pick x naught is equal to 1. From here, we can go to a nice table here. And we say, all right, we decided that x naught is going to be equal to 1. Therefore, we can start calculating everything. So the first thing that we needed in order to determine h was, of course, f of x naught. Well, that's simple. I just throw 1 into the equation, so it's going to be 1 squared minus 2. I have negative 1. Similarly, for the partial derivative, or in this case it's just the derivative since it's only a function of x, we can substitute 1 into that equation, so 2x, so 2 times 1. We know that that is going to be 2. Therefore, since we now know f of x as well as f prime of x, we can figure out h, which is going to be 0.5, and therefore that leads us to x naught plus h as 1.5. So what exactly happened here? Well, we assumed an initial value of 1. What we did is then we calculated h, which brought us over a distance of 0.5, and we are now at 1.5. All right, so we're getting a little bit closer to that square root of 2, and we say, all right, well, we're not quite at the square root of 2. So square root of 2, it's 1.4 something, 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 so we're getting closer, but we're not quite there yet. So what do? Well, we do another iteration. So our x naught before was 1. Well, now let's pick x naught is equal to 1.5. So this was the end result of our first iteration. We now bring that down, and this will be the first result, or sorry, the first guess of our second iteration. So now that it's 1.5, we can figure out f of x, f prime of x, our new h, as well as our next x naught plus h. So if we look at the graph, we basically went up again and then over to the side. So as you guys are going to see, we're going to start approaching that square root of 2. All right, and we say, you know what, square root of 2, not quite there yet. Let's do another iteration. So what I'm going to do is I'm going to have that x naught plus h from my second iteration. I'm going to have that as my initial guess for my third iteration. And as you guys can see, I end up with 1.414. So if we look here, we can see that x naught plus h, that column there, it's slowly approaching the square root of 2. But the whole point of this exercise isn't to show you this method really quick. It's more to show you guys one thing. And I'm going to ask you guys a question, that is this. Will this approximation ever be exactly equal to the square root of 2? What do you guys think? You guys can just write in the chat, yes, no. All right, so Bryce says no. What do you guys think? Hannah says yes. So I'm getting a couple of everything. More no's than yeses, and the correct answer is no. there's no way that we can numerically get the square root of 2. The square root of 2 goes on and on and on. What's going to happen as we do more iterations is we're going to get closer and closer to the square root of 2, but it'll never actually be the square root of 2. So we say that this solution approaches the square root of 2. So this is a way of approximating the square root of 2. But when we're doing FEA and analysis like this, we have to keep in mind that we will not always get the exact solution. All right. So my next question to you guys, again in the chat, just yes or no, is it ever possible to get the exact solution from approximation methods? What do you guys think? Is it possible to get the exact solution? Or will it always be just an approximation? More difficult question. So the answer is depends on the problem. And that's exactly correct. It depends on the problem. So if I were to say that x squared is equal to, let's say, 2.40, something very defined, it's actually equal to, no, let's say that I have x squared is equal to 4. Square root of 4 is simply just 2. I can achieve 2 using this method. So it does depend on the problem. But the goal here is to show you guys that, hey, you know what? Sometimes we'll never achieve that exact solution. What we want to do is approximate it. So if I'm looking at this problem and I take a step back and I end up with my approximation being 1.414, well, that's pretty close to the square root of 2. I'm pretty happy. So that's what we're doing in this finite element method, is we're going to take a lot of problems that really don't have a solution. Or if they have a solution, they're very, very difficult to obtain. And what we're going to do is we're going to approximate them. Now, of course, this is going to have a lot of problems because let's say that we didn't know the solution to something. Let's say that we look at x squared is equal to 2 and we somehow didn't know that it is equal to the square root of 2. If I'm looking at 1.5 there, it's easy to say, well, 1.5 is kind of close to the square root of 2. But if I didn't know that the solution was the square root of 2, it's very difficult to see if 1.5 is the correct answer or not. So these are some of the problems that we're going to address in the finite element method. How do we make sure that we're on the right track to getting the correct answer or approximating the correct answer? All right, so if we look at numerical analysis in FEA, numerical analysis as defined by Wikipedia is the numerical analysis is the study of algorithms that use numerical approximations as opposed to symbolic manipulations for the problems of mathematical analysis. Now, why is this important? Well, FEA is a type of numerical analysis method to find approximate solutions for displacements, stresses, and strains that satisfy the differential form of Newton's equation of motion. Now, the key here to you guys, and I really want to emphasize this because for some reason the undergrads never seem to comprehend this, we are dealing with approximate solutions. Now, again, there are very rare cases where our approximate solution is going to be our exact solution. However, for the most part, we are dealing with approximate solutions in this course. I want to emphasize that. All right? So, what we're going to do is we're actually going to utilize the weak form of partial differential equations. As you guys are going to see, the finite element method, what we're basically going to do is we're going to solve the equations of motions, which is a partial differential equation, which the solution is either A, very, very difficult to obtain, or B, impossible to obtain. So what we're going to do is we are going to take those partial differential equations, we are going to utilize the weak formulation to linearize these partial differential equations, and then we can solve them using numerical methods. As you guys are going to see, it's going to be quite a beautiful process. And if you guys are saying, Clayton, I have no idea what you're talking about right now, don't worry, it'll come. All right, so we're going to do a quick little topic of what we're going to be covering in this course so you guys can see exactly what you guys are dealing with. So, as I just mentioned, we are linearizing these differential equations. So, of course, we are going to have to do a little bit of linear algebra review, which we're going to cover in the lecture today. Again, please don't hate me. I know it's pretty boring, but it needs to be done. After that, we're going to talk about solid mechanics. It's a prereq, so again, most of you guys already know solid mechanics. But for those of you guys who don't, we're just going to discuss solid mechanics really quick. And this will give us an introduction into things like the stress tensor, the strain tensor, constitutive relationships, stuff like that. As you guys are going to see, no matter what problem you guys deal with in the finite element method, one of the key steps is utilizing relationships between stresses and strains. So we're going to talk about that in solid mechanics review. Then we're going to get into the actual fun stuff. The first one we're going to do is approximation methods. So this is kind of vague right here. Approximation methods, this could be FEA, this could be anything. In topic 3 specifically, we're going to talk about ways of approximating the exact solution of beams. So in that sense, it's still going to be a continua, or we're still going to approximate every point along the beam. We're not discretizing the beam yet. As you guys are probably aware of finite element methods, what we do is we actually discretize the beam or whatever structure you're dealing with into specific points and solve them at each specific point. So that's what we're going to talk about actually in topic 4. So topic 4, this is when we actually get into the fun stuff, the actual finite element analysis. And if you guys have taken any course, they always start simple. You got to walk before you can run. And in this case, this is going to be simple, one-dimensional finite element analysis. And if you guys have taken 660, which is advanced structural analysis, that matrix method that you guys have learned in 660, that is actually a version of the finite element method, a very simplistic version, of course. And you guys will see that it has a lot of similarities with topic number 4. Now, where things start to get a little bit different is topic 5, where we start discussing 2D and 3D finite element analysis. Of course, one-dimensional things like trusses, they're very, very easy. You almost don't even need the finite element method for them. However, for 2D things, this is where things start getting a little bit more complex, and especially when we get into 3D. So in topic 5 here, this is going to be kind of the meat and potatoes of this course. We're going to talk about how to get the stiffnesses of solid elements. For those of you who have taken 660, which is structural analysis, you guys know that we can very easily solve for displacements or forces if we know the stiffness of our structure. That's going to be the topic of topic 5, finding the stiffness of solid elements. Again, if you guys take 660, you guys know the stiffness of beam elements, but you guys don't quite know the stiffness of solid elements yet. So after that, we're going to talk about isoperimetric elements, and that's basically taking the elements that we discussed in topic number 5 here and reducing the computational effort. So as you guys are going to see, when we calculate the stiffness in topic number 5, it's going to be very cumbersome. It's not going to be a lot of fun. It's going to be very math heavy. But in topic number 6, isoperimetric, we introduce a method to easily calculate the stiffness of those elements by using reduced forms of integration. After that, we're going to talk about the Newton-Raphson method, which is actually what we showed in the introduction there. So it's kind of hard to believe, but that is actually the Newton-Raphson method in a very simplistic form. But we're going to show you guys the Newton-Raphson method for solving matrices. So it's a little bit different, but still going to be a lot of fun. After that, we're going to talk about material models, which is plasticity models, because of course, if something is linear elastic, you guys know exactly what to do. So we're going to talk about the more complex version, which is plasticity. So if you guys have taken solid mechanics, I'm sure that you guys have seen plasticity for steel. However, in this course, I'm going to show you guys also plasticity for concrete. It gets a little bit more complex, that being said, but we're going to be focusing on abacus. So once we get to topic 8 here, and this is going to be important, we're going to show you guys how to implement these things in the finite element program. So this is where everything starts to shift more from a theoretical aspect to more of a applications-based aspect, where the material models, I'm not going to ask you guys for the theory of them. It gets way too long, way too complex, and it's just kind of boring. So what we're going to do is we're going to show you guys how to implement these material models in abacus. So let's say you're doing concrete as a thesis. I'm going to show you guys how to model concrete in abacus. So perhaps if you guys, again, are doing it for your thesis, you guys might be able to get ahead a little bit. The second thing we're going to talk about is, of course, constraints and contact. Life would be really nice if we were dealing with one specific beam or one specific plate. However, reality, of course, is not very nice, and we usually have a collection of things. For instance, in my thesis, I did masonry structures. Masonry, of course, deals with a lot of different things. We have the mortar, we have the grout, we have the steel, we have the block. So what we're going to actually have to do is talk about how we can connect these things in the finite element program. Now again, topic number 9 here, this is going to be more abacus based. I'm going to show you guys how we do this in abacus. If you guys are doing, let's say, a steel beam and you guys have some bolts, I'm going to show you guys how to put the bolts into your model, stuff like that. So you guys should be good to go. Now, the last thing that we're going to talk about, of course, is instability. This has to deal mostly with the softening behavior of metals or concrete. So, of course, when you guys load something, it goes nice and up, perhaps in a parabolic fashion. But we also know that at some point it starts coming back down. That coming back down part, that's going to be the instability part that we are going to talk about. And this is one of the main advantages of finite element programs, is we're actually able to capture that instability, that softening behavior. So overall, if we look at this and we were to look at this from a finite element standpoint, the finite element method, it's very, very powerful because there's so many things that we can do with it. And that's why I love Abacus, is because no matter what situation you guys can think of, you guys can model it in Abacus, which is going to be kind of the goal at the end of this course. So if I were to tell you guys right now what I want you guys to learn from this course, it's not all the theory of the finite element method. All the theory of the finite element method isn't really that fun. It's just a bunch of math. However, what you guys will be doing, whether you guys decide to become a professor, to get your PhD, or you guys decide to go work in industry with an MEng or an MSc or even a PhD, I guess, you guys will be using finite element programs. What I would like for you guys by the end of this course is to know what, in essence, is happening at the finite element level. So one of the things when you guys use a finite element program, for instance, it's going to ask you what element type you guys want. By the end of this course, I want you guys to know, hey, I picked this element, I know why I picked this element, and I know what the difference between this element and the other elements are. And this is going to be very useful for a lot of you MSc and PhD students, because I guarantee if you guys have a model and you guys are in your thesis defense and you say, you know what, I used the quadrilateral elements, the first question you guys are going to get is why. So that's going to be the goal of this course. I want to show you guys why you guys use the elements that you guys use, as well as the limitations, of course, to the elements, and as well as the analysis itself. So that's it really for the introduction. Do you guys have any questions? Again, I guess at this point it'll just be about this course. After this, we're going to get into the actual linear algebra review. So, how are you guys feeling so far? Pretty good? All right, I hear it good. All right, perfect, perfect, perfect. So again, it should be a nice, exciting course. I'm going to try and make it as fun as possible. As you guys are going to see with linear algebra, it's not very fun, but we got this. We can do it together. Should be a nice, easy time. And you guys are all really smart people, so you guys are going to look at this and say, Clayton, this is a piece of cake. What are you doing with your life? All right, so we're going to start off linear algebra review part 1. I did it as part 1, part 2. It doesn't really matter. I just put it in case you guys want a break in between. So before we begin, I guess it's already been 40 minutes. If you guys want, we can take a little bit of a break if you guys want, 5-minute break. When we get into linear algebra, again, it's very dry, so please go get yourself a nice drink. I guess it's pretty early for a nice drink. Get yourself a nice drink, a nice a sandwich or something to eat, so you guys can just relax and have to deal with this torture. So how about we just take... We'll come back at 8:45 and we'll begin the first part of linear algebra review part 1. Sound good to you guys? It'll give you guys a chance to ask me any questions too if you guys want to. Alrighty guys, welcome back. I hope you guys are nice and comfy and ready for the fun that is linear algebra. Alright, so we're going to begin. Of course, when we're talking about linear algebra, the first thing that we're going to talk about is basis and dimensions. As you guys are going to see, basis is something that can be very complex, but for our specific case, it's actually very, very simple. So if I'm talking about R2, what I'm actually talking about is a two-dimensional vector space. Why is that a two-dimensional vector space? Well, everything can be written as a linear combination of the vectors 1, 0 and the vector 0, 1. What does this look like? Well, this looks something like this. So in essence, it's just a 2D plane. So again, I got asked, am I recording this lecture? Yes, this lecture is going to be recorded and posted as soon as this lecture is done. So you guys don't have to worry. If you guys forget something, it'll all be recorded for you guys. So what exactly does this mean that everything can be written as a linear combination? Let's say that I had the vector v here, which is 3, 2. Well, this vector v can actually be decomposed into 3 multiplied by the vector 1, 0 plus 2 multiplied by the vector 0, 1. Now, these vectors that we choose, that 1, 0 and 0, 1, that's E1 and E2, these are actually called the basis vectors. So if you guys hear me talk about basis vectors, that's exactly what it is. What you guys may be more familiar with is simply the XY plane. So in this particular case, the XY plane, well, this is the E1, E2 plane. Now, just like 2D, we can actually talk about 3D. So if I talk about R3, this is a three-dimensional vector space. And just like R2 above it, this basically means that everything can be written as a linear combination of 1, 0, 0, 0, 1, 0, and 0, 0, 1. What does this look like? Well, it's going to look something like this. So if I have a vector in it, v, which is 4, -2, and 1, I can decompose this into its three parts according to those basis vectors. So I have E1, E2, and E3. So as you guys may look, you say, oh, this looks familiar too. Well, this is essentially the XYZ plane, or I guess not plane, space in this case. So this is something that you guys are very familiar with. This shouldn't be a shock. The only thing that I want to show you guys is we typically represent these as E1, E2, and E3. So if you guys see figures from here on out that says E1, E2, and E3, you guys know exactly what it means. These are what we call our basis vectors. And again, any vector in the space can be represented as a linear combination of those basis vectors. So now let's talk about linear vector spaces. A linear vector space is a set of vectors with two operations such that these axioms hold for any u, v, and w that are vectors, as well as any alpha and beta that are scalars. The first one is if I were to take a vector u and add it to a vector v in this linear vector space, well, my resultant vector will also be a part of that vector space. So this one right there, that's actually going to be very important. The second one is u plus v is going to be equal to v plus u. We have u plus, in brackets, v plus w is equal to, in brackets, u plus v plus w. We have a zero vector in this space, where if I were to add u to this zero vector, I simply get u. And finally, there is a negative version of our vector, where if I go u plus the negative version of u, it's always going to give me that zero vector. Now, if we were to look at these first 5 axioms, they all really have to deal with addition. And if you guys are confused right now, don't worry. I'm going to explain exactly what this means on the next slide. When I deal with these linear vector spaces, they're almost impossible to imagine. But once I show you guys a figure, it usually clears up a lot of things. All right. So again, we have 5 axioms that are basically have to deal with addition. However, we have more axioms, as you guys are going to see, that have to deal with multiplication. So the second one is if I were to take any scalar, alpha, so it could be 2, it could be -5, any real number, and multiply it by my vector u, well, that resultant must also be a part of that vector space. I also can take a scalar alpha and multiply it to the addition of u plus v, and I can actually decompose this into alpha u plus alpha v. If I wanted to, I can take two scalars, add them together, and then multiply by u, and this will be the same as alpha u plus beta u. I got alpha times beta u is equal to alpha beta multiplied by u, and then if I were to take my vector u, multiply by 1, I'm simply going to get u. All right, so as we can see, these second axioms have to do with multiplication. And if something satisfies all 10 of these axioms, it is a vector space or a linear vector space. So some examples of these linear vector spaces are 2. We just discussed that above. R2 is simply a vector xy, where x and y can be any scalar. So for instance, 2, -1, that works. 4, 6, that works. Another example would be R3. So again, in the last slide, we talked about R3. It's simply a vector with 3 components, x, y, z, where x, y, z can be absolutely anything. And when we're talking about vector spaces, it's hard to imagine, but if we look at these vector spaces here, R2 and R3, the main reason that they're vector spaces, or the reason it's very easy to tell when they're vector spaces, is there's really no restrictions on x and y. So again, if I look at R2, x and y could be any real number. It's when we start imposing restrictions when these start becoming non-vector spaces. So if we're trying to disprove a vector space by saying, you know what, this is not a vector space, what we basically want to do is we want to look at the top 2 axioms. The first one is that if we have 2 vectors in our vector space, u and v. If we add them together, that resultant vector must be in our vector space. So that's going to be a very important one. And the second one, alpha times u, so alpha is any real number, u is a vector, that multiplication must also be in our vector space. So what does this exactly mean? Well, let's look at an example. All right, so I'm going to show you guys two examples of invalid linear vector spaces. The first one is, let's say that I'm saying I have a linear vector space V, which is simply a vector, x and y, but I'm imposing restrictions where x has to be greater or equal to 0 and y has to be greater or equal to 0. So again, when I start looking at vector spaces that are not vector spaces, it usually comes from these restrictions. So again, R2 and R3 in the previous slide, they had no restrictions. However, now we have two restrictions, one on x and one on y. So if I were to look at this in terms of my basis vectors e1 and e2, and say, all right, well, if x is greater than 0 and y has to be greater than 0, all my vector components have to be greater than 0. So if I were to look at this plane here, all my vectors must be within this realm. For instance, a vector xy that's greater than 0, that can be something, let's say, 1, 3, a vector like this. Now, if I had a vector 1, -3, well, -3 is not greater than 0, so therefore that vector is not in the vector space. Right now, we're only dealing with vectors in our space. So we have, let's say, 1, 3, and let's say that we had a vector 3, 1. So these two vectors right here, these are within our vector space. So after that, what we do is we go through our axioms. So again, the first one that I mentioned to you guys is that the addition of two vectors within our vector space must also be within the vector space. So let's say I take this purple vector here and this blue vector and I add them together. That gives me this green vector right here. As we can see, this green vector or this resultant vector is in our vector space. So therefore axiom number 1 there, that holds. We are good to go at this point so far. Now, the second axiom, which I said to always look at, is axiom number 6, which is any multiplication by a scalar must also be within our vector space. And this is where things go bad for this particular vector space. So let's look at that purple vector right there. If I were to multiply that vector by, let's say, 2, well, the height of that vector, or the length of that vector, is simply going to expand by a factor of 2. That would still be in our vector space. But if I were to multiply that purple vector by -1, as we can see, this vector now exits our vector space. Therefore, if we multiply by a negative scalar, our vector exits the vector space. Therefore, this vector space as a whole is actually not a vector space. The reason why, it doesn't hold axiom number 6, multiplication by a scalar. Now, if we were to look at a different vector space, as say xy, where the multiplication of xy has to be greater or equal to 0, this is a little bit different. So in this particular case, the components of x and y don't necessarily have to be positive as long as the multiplication of them together is positive. Therefore, if I were to take, let's say, 2, 2, well, 2 times 2 is 4, greater than 0, good to go. If I were to say -2, -2, well, of course, -2 multiplied by -2, that's also positive 4. So in this particular case, we actually have two ways this can go. So if I were to look at that purple vector again, and I were to multiply this by -1, as we can see, we are still in our vector space, which is good to go. However, if I were to look at a second vector in this vector space, let's say this blue vector down here, and I were to add this to my purple vector, as we can see, the resultant here actually exits our vector space. So in this particular case, this is also not a vector space because the addition of two vectors can exit our vector space. So this is just an example of what a linear vector space is. But of course, for us, when we're dealing with the finite element method, we are dealing with R2 and R3. Those are linear vector spaces, so we're actually good to go. We don't have to worry too much. I just wanted to show you guys examples of what would be considered an invalid linear vector space. So the next thing that we're going to discuss is linear dependence / independence. So a set of vectors is called linearly dependent. So dependent if none of the vectors in the set can be expressed as a linear combination of the other vectors in the set. Clayton, this sounds like a bunch of gibberish. What exactly does this mean? Well, let's look at an example. I have my bases set here, E1, E2, and E3, and I have a vector in the E1, E2 plane, U, which is simply just 4, 2. And I don't know why I did two-dimensional vectors in a 3D plane. I'll have to fix that later. But the purpose of the example will still show. Just forget that I have the E3 axis there. Now let's say I have a second vector, W, which is equal to 2, -2. Now, if I were to compare the vectors u and w, it's very easy to see that these vectors are not a linear combination of one another because they have different directions. All right, so if we were to look at u and w right here, we'd see that these are linearly independent. These vectors are independent of each other. But if I had another vector, let's say v, that goes in the exact same direction as u, we would say that these vectors are now linearly dependent. Because if I were to take v, which is 2, 1, and multiply that by 2, I get the vector u, 4, 2. Now, if I were to look at w and multiply that by a number to try and get u, it would never happen. So in essence, to determine the linear dependence or independence of two vectors u and v, what we're going to do is we're going to solve the following equation, where alpha 1 times the vector u plus alpha 2 times the vector v is equal to the 0 vector. So alpha 1 and alpha 2, those are going to be our unknowns because u and v we know, the 0 vector we know, so therefore we're going to solve for alpha 1 and alpha 2. And what's going to happen is there's going to be two different possible solutions. The first one is alpha 1 is equal to alpha 2, which is equal to 0. So all of those coefficients, they're equal to 0. Therefore, our vectors are going to be linearly independent. What is alpha 1 equal to alpha 2 equal to 0? Well, that's actually the trivial solution. And I'm going to show you guys this, which will make a little bit more sense. The second one is that we have alpha 1 does not equal 0 or alpha 2 does not equal 0. So the key here is only one of them does not have to equal 0. If I get alpha 1 is equal to 1, but alpha 2 is equal to 0, they're still linearly dependent. All right, so as long as one of those coefficients do not equal 0, they are linearly dependent. So let's look at our actual examples. Let's take our vectors u and v, which we actually said are equal to, or we actually said that they're linearly dependent. Well, if I go alpha 1 multiplied by the vector 4, 2, plus alpha 2 multiplied by the vector 2, 1 is equal to 0, I actually have two solutions. Now, these solutions aren't correct, but basically we get alpha 1 and alpha 2 do not equal to 0. All right, but if we were to, and this means that they're linearly dependent. But if we were to look at the vectors u and w, alpha 1 times 4, 2, and alpha 2 times 2 and -2 is equal to 0, what we see is alpha 1 is equal to 0 and alpha 2 are equal to 0. That's the only solution in which that equation holds. Therefore, these are linearly independent. All right, so this is something that will become a fun fact later on, but this isn't something that's too critical yet. Now we're going to start talking about some linear algebra that actually applies to the finite element method. And the first one are norm functions. So norm functions, as you guys will see, this is something that you guys have actually dealt with a lot, not only in linear algebra, but in statics. So in statics, when we talked about vectors, one of the things that we talked about a lot was the magnitude of a vector or the length of a vector. That's essentially a norm function or a specific type of norm functions. As you guys will see, there's actually a lot of different norm functions. So norm functions are functions used to describe the size of vectors in a linear vector space, and it's typically denoted as the double absolute value signs v, or what I would say if I saw the symbol, this would be the norm of vector v. Now again, you guys are very used to the magnitude of these vectors, but in essence, a norm function can actually be many different functions. A norm function must satisfy for any two vectors u and v and any real scalar alpha the following traits. So first one is positive homogeneity. I can't say that word at all. I don't know why. Or positive scalability. What does this mean? Well, if I were to take the norm of alpha v, this is simply going to be the absolute value of alpha multiplied by the norm of v. The second one is the triangular inequality, which means the norm of vector u plus vector v must be less than or equal to the norm of vector u plus the norm of vector v. And the third one is positive definiteness, which means that if the norm of a vector, any vector v, is equal to 0, Well, the only way that's possible is if v is the zero vector. All right, so these are the three equations that, or the three properties that define a norm function. Now, what you guys will see is there's actually a lot of different types of norm functions that satisfy these three properties. But the one that we're going to be interested in is what we call the Euclidean norm. All right, so as you guys are going to see later, we are dealing with a Euclidean vector space. So therefore, we are dealing with the Euclidean norm. But that's good because the Euclidean norm is the one that you guys are most familiar with. So let's say that I had a vector v, which is v1, v2, all the way into vn. Right here, this is an infinite dimension vector. However, of course, we are dealing with R3, so we would just have v1, v2, and v3, nice and simple. But in general, a vector v, the norm of vector v can be found by square rooting v1 squared plus v2 squared plus dot 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 vn squared. So this is what you guys are used to. This is what we've called the magnitude of a vector. And if we look right here and we look at this norm function, we can see that this norm function will always be a positive scalar for non-zero vectors. There is no way that you guys can have a norm here that's equal to, let's say, -2. And that's good because let's say that you're doing your calculations and you get -2, you go, oh, wait a second. I did something wrong. I should probably recalculate. So again, this is the norm function you guys are probably most used to. But what exactly does this mean? Well, let's say that I had in R3 a vector v, which is 4, -2, and 1. Well, I can calculate the norm of this vector. So it's just going to be all the components squared, added together, and then square rooted. So I'm going to go 4 squared plus -2 squared plus 1 squared, square root it. And I get the norm of this vector is equal to around 4.583. What exactly does this mean? Well, this means that the length of that vector there is around 4.583 units. Now you may be saying, all right, Clayton, this is nice, simple, fun stuff. What does this have to do with the finite element method? Well, norm functions, again, describe the size of vectors. And as we saw when we did that little example for finding the square root of 2, we went from 1.5 to 1.417 to 1.414. The size of that was decreasing. So what we do is we use these norm functions in the finite element analysis to figure out if our results are converging upon a specific value. Because if something's converging, then the difference starts to become really small. How do we find the size of that? How do we find how small it's becoming? Well, we use these norm functions. So this is why these are going to be particularly important in the finite element analysis. The second one that we have is a metric or a distance function. So a metric function are used to find the distance between any two vectors in a linear vector space and is denoted as rho of u and v. So this basically means the distance between vectors u as well as vector v. And just like a norm function, these actually have a lot of different possibilities. So what we do is we say, all right, well, a metric function must satisfy for any three vectors. First one, symmetry. What exactly does this mean? Well, if I were to go the distance between vector u and vector v, this is the exact same as the distance between vector v and vector u. What exactly does this mean in sort of a more practical aspect? Well, if I were to go from Edmonton to Calgary, that's the same distance as going from Calgary to Edmonton. It shouldn't change depending on which direction you guys go. The second one is the triangular inequality. So the distance between vectors u and w must be less than the distance between vector u and v plus the vector v to w. And then finally, the second one is the distance between vectors u and v. If that is equal to 0, the only way that is possible is that the vector u and the vector v are the exact same vector. So like the norm function, there are many different types of functions that actually satisfy these three properties. But the one we're going to be looking at is the Euclidean distance. And this is very easy to memorize because we deal with the Euclidean norm. Now we're dealing with the Euclidean distance. Just put Euclidean in front of everything. You guys will be good to go for finite element analysis. So let's look at an example of what this Euclidean distance function is. If I had two vectors, u and v, in this case, they're all the way up into dimension n, but of course we only deal with R3, so they're not going to be this complicated. The distance between u and v is simply going to be the norm of u minus v. You say, Clayton, well, that looks kind of complicated. What exactly does this mean? Well, we can simplify this into the square root of u1 minus v1 squared plus u2 minus v2 squared plus un minus vn squared. So nice and easy. Let's look at a little example here. I have two vectors in 2D. My first one v, which is 4, comma 1. My second one u, which is 2, comma negative 1. What I can do is I can say the distance between these two vectors is going to be 2 minus 4 squared plus negative 1 minus 1 squared. And I get that the distance is 2.828. What exactly does this mean in terms of the picture? Well, this is the distance between the two tips of those vectors. So again, not something particularly crazy to comprehend, but going to be very useful moving forward. Now, the next one that we're going to talk about is the Euclidean dot product, and this is going to be one of the more important ones moving forward. So the Euclidean dot product is an example of an inner product function and is denoted as x dot y, or I guess u dot v. I forgot to change that, which is the dot product between vectors u and vector v. Now, my question for you guys really quick is, what is an inner product function? Do you guys, any of you guys know what an inner product function is? What do you guys think? I'm only doing this because I need a quick drink break. My throat's getting... So I hear that it's a scalar. That is correct. But what is an inner product function used for? For instance, the norm function we know was to describe the size of a vector. The metric function was used to describe the distance between two vectors. What does an inner product function used for? What do you guys think? Little fun fact while I have a little drink. All right, so I hear projection, and that's definitely one of the cases. So yes, what a norm function basically wants to tell us is the relationship between two vectors in a linear vector space. So if we're looking at the dot product here, where we have a vector u and a vector v, the dot product between these two vectors, u dot v, is very simple. I take the components, multiply them together, and then add them all up. So if I were to look at u dot v, it's going to be u1 multiplied by v1 plus u2 multiplied by v2 plus dot 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 un multiplied by vn. And as one of you guys have said in the chat here, this will give us a scalar. And this is very important to notice. We take two vectors, so we start off with two vectors, and we end up with the scalar. Now, again, what an inner product function is, it tells us a relationship between two vectors. In this case, when we're talking about a Euclidean dot product in 2 and 3 dimensions, this dot product is actually used to relate the geometric angle between two vectors. So we said that we had our dot product, which is equal to u1 times v1 plus u2 times v2, etc., etc. Well, this is actually equal to the magnitude, or the norm of u, multiplied by the norm of v, multiplied by cosine of theta. Now, if we look there, that theta there, that's the angle between the two vectors. And this is what makes the dot product an inner product function, is because it tells us a relationship between these two vectors. So from this formula here, we can actually rearrange it, and we get cosine of theta is equal to u dot v divided by the norm of u multiplied by the norm of v. So what exactly does this look like? Well, let's say that we have two vectors yet again. Exact same vectors from before, where v is 4, comma 1 and u is 2, comma negative 1. Well, what we can do is we can say that cosine of theta is equal to the dot product, so 4 times 2 plus 1 times negative 1 divided by the norm of v divided by the norm of u. Therefore, we can actually solve for theta, which is 40.6 degrees. That means that our angle here between these two vectors is 40.6 degrees. So that's what an inner product function is, or more specifically for us, our Euclidean dot product. It gives us a nice relationship, a geometric relationship between two vectors in the space. All right, so why am I telling you guys this? Why am I telling you guys about Euclidean norm, Euclidean distance, and Euclidean dot product? Well, this leads us to, oh, I forgot about some properties. I'll get to what I was saying in 2 seconds. We're just going to talk about these properties, and these are actually going to be very important, more specifically for the proofs. So we're going to actually deal with a lot of proofs when we get to the solid mechanics section, and a lot of those proofs are actually obtained using these properties. So if we had two vectors u and v which are orthogonal or perpendicular to each other, then u dot v is equal to 0. So this is if they are orthogonal or perpendicular to each other. And this is very easy to see, because if we look at this formula here, we have that cosine of theta, and if we know something is orthogonal or perpendicular, theta is equal to 90 degrees. Therefore, cosine of 90, well, that's going to be 0. Therefore, u dot v divided by the norms of the two vectors can be equal to 0. I can move the norms to the other side, 0. U dot v must be equal to 0. Now, a second property that we're going to also have to deal with is a vector dotted with itself. This is actually very important when we talk about proofs for the strain tensor. A vector dotted with itself, u dot u, is equal to the magnitude of u squared. And again, this is very easy to see. We go back to our formula here. We look at that cosine of theta and we say, oh, if it's the same vector, well, the angle between them is going to be 0 degrees. Therefore, cosine of 0 is going to be equal to 1. We have u dot u divided by the magnitude is equal to 1. Move it to the other side. We have u dot u is equal to the magnitude of u multiplied by the magnitude of u. Well, that's just going to be the norm of u, or the magnitude of u squared. So these are two properties. Nice little fun properties, but something you guys shouldn't have to memorize. They're fairly self-explanatory once you guys get into the math of it. Now, as I was saying before, why am I telling you guys all this? Why am I telling you about Euclidean norm, Euclidean distance, and Euclidean dot product? Well, it leads us to Euclidean vector space. Now, what is Euclidean vector space? Well, Euclidean vector space is a vector space equipped with three things. As you guys may have guessed, Euclidean norm, Euclidean distance, and Euclidean dot product. So if those three functions are used in the vector space, we say that we have a Euclidean vector space, which was discussed above. Now, why is this so important? Why do I want a Euclidean vector space? Well, from a Euclidean vector space, I can actually form the following: an orthonormal basis set, orthogonal projections, cross product, as well as triple product. And these are going to be very useful moving forward. So we're going to talk about each one of these. The first one is going to be an orthonormal basis. And this is something that you guys may have not been realizing, but we've been dealing with this basically our entire lives of engineering. So an orthonormal basis set is a basis set B, which is E1, E2, and E3. So we talked about E1, E2, and E3 before, whose vectors, A, have a unit norm. So if I were to look at E1, E2, and E3, the norm of each one of those vectors must be equal to 1. So if we were to look at our vectors before where we had 1, 0, 0, well, it's easy to see that those norms are actually equal to 1. It's very nice. All right. And the second property is the vectors, all three of them, E1, E2, and E3, are orthogonal to each other. So they're all perpendicular to each other. So we have E1.E2 is equal to E1.E3, which is equal to E2.E3, which is all equal to 0. So an example of an orthonormal basis set is going to be the most trivial one that you guys have dealt with your entire lives. E1 is 1, 0, 0, E2 is 0, 1, 0, and E3 is 0, 0, 1. And we can see that this is basically our simple coordinate system that we've always dealt with. So look familiar? Well, of course. You guys have seen this a million times. Piece of cake. But there are others. So even though we deal with this one because it's most simplistic, we must realize that there are actually others. So in example number 2, we can have E1 as 1 over the square root of 2, comma, 1 over the square root of 2, comma, 0. So if I were to take the norm of that, it's actually equal to 1. So that's satisfied. And then E2 is the exact same thing, except we have a negative 1 over square root of 2. And then E3 is 0, 0, 1. What would that look like? Well, it looked like the exact same thing, except E1 and E2 are now rotated. But this is a perfectly valid orthonormal basis set. All the vectors are perpendicular to each other, and the norm of each one of those vectors is actually equal to 1. And we're going to talk about this a little bit more when we talk about change of basis and why this is so important. So in essence, we may look at this and say, Clayton, well, of course, I'm always going to go with example 1. It's the most simplistic. But sometimes we actually may have to go to example number 2. And I'll tell you guys a little bit why later on. So the second thing that we can then define are orthogonal projections. So an orthogonal projection, not orthonormal, an orthogonal projection of vector u onto v can be used to determine the components of vector v in the direction of vector u. Now, if we look at this, you say, Clayton, again, what's with all the words? Make it simple. Well, let's look at this. Let's say that we have a vector in 2D space, e1 and e2, and it has components u1 and u2. If I were to say to you guys, what is the components of u1 in the direction of e1? Well, it's very simple. U1 is simply, the component is simply going to be U1. We know that this vector U has a component in the direction of E1 of U1. If I were to ask you guys what is the component of this vector in the direction E2, well, that's also very simple. It's just simply going to be U2. So what are we dealing with projections? Well, let's say I ask you guys, what is the component of that vector U in the direction of V? So this is where it gets a little bit more complex, because if we look at the components U1 and U2, well, that doesn't tell us the components of this vector onto vector V. So what I want to do is I want to find a way to have a relationship between U and V so that I can determine the components of U onto vector V. So that'd be that blue vector right there. Luckily for us, we have a very nice formula for this, where the projection of U onto V, which I'm going to call vector A in this case, is simply going to be U dot V divided by the magnitude of U divided by the norm of V multiplied by that vector V. The key here is this vector A is going to be parallel to V. Now, what they do in statics or Eng 130, that beginner level engineering class, is they trick students and they say, you know what, A is nice. I like A, but I don't care about A. I'd rather have this vector right here, which is perpendicular to V. So what I'm going to do is I'm going to call this vector right here B. And as we can see, we look at U. U is simply the composition of A plus B. So therefore, I can solve for this perpendicular vector B as simply U minus A. And this vector, of course, is perpendicular to V. All right, so we look at this. We say this is not that bad. So let's do a quick example of an orthogonal projection of U onto V. With this example, I want to show you guys kind of the secret here. We have two vectors, V, and we have U, so they're the same components as we've seen before. And if I wanted that orthogonal projection A, well, it's very simple. I got 4 times 2, because it's the dot product, plus 1 times -1, divided by the norm of U, which is the square root of 17, divided by the norm of V, which is square root of 5, and we multiply this by vector V, so 4, 1. What happens here is all that in the brackets there, that becomes a scalar. And we're taking a scalar and we're multiplying it by a vector. So the result here for A is a vector. And this is very important to notice. A lot of Eng 130 kids, they somehow make this a scalar. I don't know how, but they, they managed to do it. One of the things I want to ask you guys here is, does the order matter? Is the projection of U onto V the same as the projection of V onto U? What do you guys think? All right, I hear a no. Any other takers with the no? All right, got another no. All right, perfect. You guys are completely correct. So the order does matter, and that's why on this slide here, I have it underlined, U onto V. If we were to switch it around and go V onto U, well, it's going to be the exact same thing. If we look at the formulation, the only difference is instead of multiplying by vector V at the end, we have to multiply by vector U. So just a little fun fact. So the next thing that we're going to discuss is the cross product. And this is something that you guys have probably seen before, or not I think at this point you guys have definitely seen this before. If not, then I don't know how you guys did statics, really. All right. So the cross product is a unique operation in R3 between two vectors U and V that returns a third vector W that is perpendicular to both vectors U and V. So if we look here, it says that the cross product is a unique operation in R3. And that's very important. We can only do it in R3 because we can't do it in R2. We can't do it in simply R. We can't do it in R4. My question to you guys, again, really quick, because I need another drink. My voice is getting a little bit dry. Is there any other dimension in which we can do the cross product? What do you guys think? We can do it in R3, but we can't do it in R4. We can't do it in R2. Is there any other dimension that we can do the cross product in besides R3? Weird question, I know. It's more of a little fun fact, not something you guys need to know. But the cross product is actually valid in R7. Don't ask me how. I'm not a linear algebra guy, but somehow it's valid in R7. Just a little fun fact. Why is that just a fun fact and not something we care about? Because again, when we're dealing with finite element analysis, we're dealing with practical stuff. We're engineers, we're not mathematicians. The most we'll ever get to is R3. If you guys are designing a building for R4, then there's probably something a little bit wrong. All right, so for us, the cross product is a unique operation in R3. And again, the whole goal here is we get a vector that's perpendicular to vectors u and v. So if I have my two vectors here, u and v, and I cross them together, what happens is I get a third vector, w, which is perpendicular to both u and v. What is the formulation for this? Well, w, which we say is equal to u cross v, is simply that. u2 multiplied by v3 minus u3 multiplied by v2. And I just kept it simple here. Now, the reason why I kept it simple is because, as I've learned from statics, there are so many different ways to do this damn cross product. In the statics course here at the University of Alberta, I would teach my section one version of the cross product, but everyone else taught their own section a different version of how to calculate the cross product. So it's weird. If I had a student from a different section asking me questions, I'd be like, I have no idea what you're doing, but you're somehow getting the answer. There's many different ways to calculate this cross product. Now, you guys don't really have to do it because luckily for you in this course, we're going to deal with computer programs and they do it for us. It's very nice. But the key takeaway here is that this returns us with a vector. Okay, if you guys get a scalar from this, again, something's wrong. Now, a couple little fun facts. W is perpendicular to the plane created by u and v. That's going to be very important when we start talking about the proofs presented later on in the solid mechanics section. Now, there is another little fun fact in which the magnitude of W is actually related to u and v. So if we look at u and v, they actually create a parallelogram. And the area of that parallelogram is equal to the norm of that cross product vector W. So that's another little fun fact that we'll use in our proofs for solid mechanics. Now, I'm not going to try and fool you guys at all. I'm going to be completely honest with you guys. I'm not going to test you on any proofs. Proofs are a nightmare to get on a test. No one likes a proof on a test. It's a surefire way to hate your professor. I don't want that at all. What I'm going to do is I'm going to show you guys the proofs for solid mechanics, as I've been saying, but I will never test you guys on that. So if you guys are worried about proofs, don't worry about it. This is just supplementary information so that when I show you guys the proofs, you guys, oh, okay, that's what he was talking about. Okay, that makes sense. But I won't test you guys on proofs, so please don't worry about that. All right, so we're going to look at some of the cross product properties. The first one, of course, the resultant vector W is perpendicular to u and v. What exactly does this mean? Well, w dot u is equal to w dot v, which is equal to 0, because of course they're perpendicular. The operation is skew symmetric, which means that u cross v is equal to negative v cross u, and that's very important. One of the things, again, the statics kids love to do is they say that u cross v is equal to v cross u. Then they get the answer wrong. Then they show up at my office saying, why did I get it wrong? And it's an absolute nightmare. Now, another one is the operation is distributed over addition. Therefore, u cross v plus w is equal to u cross v plus u cross w. The operation is compatible with scalar multiplication. So alpha u cross v is equal to alpha of u cross v, which is equal to u of v times alpha. And then finally, we have this big long proof. Just more, again, little fun fact. You guys don't really need to know it that much. All right, so let's look at some cross product scenarios right here. So cross product of basis vectors. This is very nice. And if you guys look at any sort of continuum mechanics or solid mechanics textbook, it'll always have these ones right here. So if we were to look at E1 and E2, we said that we deal with orthonormal basis sets. Therefore, all three of our vectors in 3D are perpendicular to each other. So if I were to go E1 cross E2, I'm getting plus or minus E3. Similarly, if I were to go E2 cross E3, I'd get E1. And finally, if I were to go E1 cross E3, I'm actually able to get E2. So that's, again, more of a proof thing that you guys will see in a lot of continuum mechanics textbooks. Not very important. It's very easy to see. The second one, of course, is the cross product of linearly dependent vectors. So remember, when we talked about linearly dependent vectors, they have the exact same direction. What does this mean in terms of the cross product? Well, u cross v is actually equal to 0. This occurs if three things: u is equal to 0, or v is equal to 0, or u is equal to some scalar multiple of v. And it's very easy to see. If we were to put these two vectors together and they are linearly dependent, that means they have the same direction, therefore they form no sort of parallelogram. And it's very easy to see because if I were to have just a line in 3D, well, there's infinite possibility of vectors that are perpendicular to that line. It basically goes around in an entire circle. So it's, again, very easy to see. And again, something that we'll use a lot when we start talking about proofs. All right, so the next one we're going to talk about is the triple product, or I've also seen it called the triple scalar product. And this is, again, something used in proofs. And what this basically is the volume of a parallel pipe created from the vectors u, v, and w, which is quite simple. So what happens is what the triple product is equal to is we have three vectors, u, v, and w. It's going to be u dotted with v cross w. Again, nice little proof here. Something we'll use in the proofs, but not very, not very special. Triple product properties. We have basically three of them, and they're not too crazy. The last, I guess the one that you guys will want to know is u, v, and w are orthonormal. Then the triple product is equal to plus or minus 1. And we're going to talk about that a little bit more when we go to linear maps. But triple product isn't something you guys will see that often, so I wouldn't worry about it. Now, the last thing that we're going to talk about in this section before we take a little bit of a break, I know you guys probably need a little bit of a break from this snooze fest, but please pay attention because this last one is actually going to be important. And that is a change of basis. So, the components of a vector depend on the selected set of basis vectors. So normally we pick 1, 0, 0, 0, 1, 0, and 0, 0, 1. But as I showed you guys, we can actually pick different sets of orthonormal basis. And in some scenarios, it's actually necessary to transform the coordinate system, like I said. We'd like to pick example 1 with the 1, 0, 0, etc., etc. But sometimes we actually have to change it depending on the example. And you say, Clayton, well, give me an example of that. Well, let's take material properties of something. What we do when we measure material properties is we measure them in certain directions. The best example is wood. You guys know that wood have those nice vertical fibers. Therefore, we actually have to measure along that vertical line and then perpendicular to it. So if we were to load a piece of wood in a direction that's not aligned with those wood grains, what we actually have to do is we have to transform our load to match the direction of those wood grains. Now, this is something I'll show you guys a lot more in depth later. I'm just trying to show you guys what exactly this means. But let's just look at a change of basis. So let's say that I'm hanging out my basis set of E1 and E2, the most trivial one, 1, 0 and 0, 1. And I have a vector U, which is equal to 3, 2. And I say, well, you know, this is fun. I'm having a great time. But let's change the basis set. So what I'm going to do is I'm going to apply a transformation matrix Q, and we're going to talk more about Q in the coming slides, so that'll actually rotate my basis set. So now instead of E1 and E2, my basis set is now E1 prime and E2 prime. The key takeaway I want to show you guys right here, U did not change. My vector U, it remained static. It did not move at all. I just moved my basis set. Now, even though U did not change, since I moved my basis set, it's very easy to see that U is going to have different components. So now U prime is not equal to 3, 2. It's equal to 3.54 and negative 0.72. So the question becomes, what is the relationship between U and U prime? Well, it's very easy to see that there is a nice relationship where U prime is simply Q, which is our coordinate transformation matrix, multiplied by our original vector U from the original basis set. So if we look at this, we say, all right, well, I can figure out what U prime is if we know both Q, the transformation matrix, and U, which is our vector in the original basis set. Now, when we deal with these sort of problems, we definitely know what U is. That's what we start off with. The question is, well, what is Q? Well, Q, as I said, is our coordinate transformation matrix. So the coordinate transformation matrix Q can be calculated from the two basis sets. So again, it's a matrix, so it's going to have components. Each component, which is qij, is simply going to be the dot product of ei prime. So this is going to be the basis vector in the transformed basis, dotted with ej. Looking at this formula is a nightmare. You look at this and say, I don't know what the hell this means. So let's do an example. A 2D counterclockwise rotation. So again, we have our nice normal basis set. We have E1 is 1, 0, and we have E2 is 0, 1, and we apply our coordinate transformation matrix to rotate this counterclockwise in the 2D fashion. How much do we rotate it by? Well, let's just keep it arbitrary. Let's say we rotate it by a magnitude of theta. So if we look at the formula for Q above that transformation matrix, as we can see, it's dependent on those basis vectors, E1 prime and E2 prime. So we need to figure out what E1 prime and E2 prime is, but it's actually very simple. It looks gross, but it's actually very simple. E1 prime can be found using a simple right triangle. So if I were to look at the components of E1 prime in the x direction, it's going to be 1 because, again, all of our basis sets must have a norm of 1, so that magnitude of that black line is 1, which is the hypotenuse, multiplied by cosine of theta. That gives us that nice x component. If I were to look at the y component of E1 prime, it's going to be 1 again because that's the hypotenuse, multiplied by sine of theta. Therefore, E1 prime is simply cosine of theta, comma, sine of theta. Nice and easy. Similarly, we can look at E2 prime. We look at the x direction and we say, oh, hold on 1 second. This is now going left instead of going, or sorry, this is going to the left. Therefore, we know that it's going in a negative direction, and the magnitude of this is going to be 1 multiplied by sine theta. Similarly, E2 prime in the y direction is going to be 1 multiplied by cosine of theta. Therefore, our E2 prime is equal to negative sine theta and then cosine of theta. Nice and easy. So what do we do to find our coordinate transformation matrix U? Well, to find each component, all we have to do is do the dot product between a bunch of these basis vectors. So if I'm looking at Q11, well, we just look at our formula. So we have E1 prime dotted with E1. Well, that's going to be cosine of theta multiplied by 1 plus sine of theta times 0, which is just going to be cosine of theta. Now, if I were to look at Q22, we have E2 prime dotted with E2. This is going to be negative sine of theta times 0 plus cosine of theta times 1. Well, that's just going to be cosine of theta. Similarly, I can do it for Q12, which is going to be sine of theta, and Q21, which is going to be negative sine of theta, and I now know all of my coordinates. So therefore, my coordinate transformation matrix for a 2D counterclockwise rotation is simply just going to be cosine of theta, sine theta, and then negative sine theta, cosine of theta. So it should be nice and easy because even if you guys were to have a 3D example, you guys can very easily find the components of the basis set E1 prime, E2 prime, and E3 prime, and then you guys can find all of the coordinates of the transformation matrix. Now the nice thing about this is it always remains the same. So if you guys were to find a Q for a counterclockwise rotation and Q for a clockwise rotation, just write them down. If you guys ever have an exam scenario and it asks you for them, well, then you guys won't have to derive them. You guys can just look at your little cheat sheet, say, oh, I'm dealing with a counterclockwise rotation, therefore I'm going to use this following coordinate transformation matrix. Now, in this particular course, you probably won't have to use them too much. This will come more in handy in solid mechanics, but you never know, so it's good to know. And with that being said, that concludes our review of part 1 of linear algebra. So that had to do with linear vector spaces. Now moving forward, we're going to get into the review part 2, which is the last part of this lecture. And this has to deal with linear maps. So at the very end there, I showed you a coordinate transformation matrix. We're going to now talk about what exactly a matrix is, and an extension of it, what exactly a tensor is. So I'm sure that you guys have heard the word matrix a million times. Some of you may have heard what a tensor is. For this particular course, spoiler alert, they're the exact same thing for this particular course. But that's what we're going to talk about next. But it's a lot to take in. Linear algebra, again, very boring, nothing too special. So what we're going to do is we're going to take another 5-minute break, refill your drinks, get comfy again, grab a blanket if you're cold, grab a snack, something like that. I will see you guys back at 9:40. All right, guys? All right, I'm getting nothing, which is either a very good thing or a very bad thing. I guess we'll find out next lecture. All right, so we're going to continue on. Now we're going to talk about our linear algebra review part 2. And in this case, we're going to be talking about linear maps. Now, linear maps are something in linear algebra that start off really simple. We can really see what it means. But as you guys will see when we talk about the finite element method, it's very, very important because essentially we have one giant linear map. For instance, if I have my beam and my boundary conditions, those are basically my inputs. I put them into my linear map, and then it outputs me with deflections, stresses, stuff like that. So it's going to be very important moving forward. But again, before we can run, we have to walk. Well, actually, linear algebra is more the crawl. Solid mechanics is the walk, and then the finite element method is going to be the run. So we're going to move on forward. I just got to click. All right, perfect. So linear maps. By definition, a linear map T between two vector spaces v and w is a function for any vectors u and v and any scalars alpha and beta, where t of alpha plus u is equal to beta plus v is equal to alpha tu plus beta tv. Now, this may sound a little bit confusing, but I'm banking on the fact that you guys already know what linear maps are. They're basically matrices. All right, you guys have seen matrices all the time. So one example, f, which goes from r to r, fairly simple. F of x is equal to alpha of x. Now let's say that f of x is equal to 7x. Well, therefore, f of 2 is equal to 7 times 2, which is equal to 14. So when you guys think about matrices before, I'm not really sure how you guys think of it, but this is how I want you guys to think about these matrices or these linear maps. We have an input, which is an r, and in this case, our input is 2. X is equal to 2. What we do is we throw that into our linear map. In this case, it's 7x. So in this case, we have 7 times 2. And we are given an output, which is 14. And now if we look at this, our output is again in R. That's why our example is from R to R. We input something from a real number. We're outputted with a real number. Now example 2 here, we have R2 to R2. So this is 2 dimensions to 2 dimensions. So an example of a linear map with this would be the matrix C alpha 1, 1, alpha 1, 2, alpha 2, 1, and alpha 2, 2 multiplied by the vector x1, x2. So let's say that our linear map in this case was 7, 1, and then 4, negative 2. What I can do is I can say, all right, well, if I input a vector, let's say 1, 2, I can get an output vector of 9, 0. So again, we have an input, which is in R2. We throw that bad boy into our linear map, and then we're outputted with 9, 0. And again, this is what the finite element is. We input what our boundary conditions are, our material properties, all that stuff, and then we are outputted with stuff like displacements, strains, stresses. But as you guys can imagine, we have a lot to input and we have a lot to output. So the map in between, that's what we're going to be focusing on in this course. How do we get this map? Now, linear maps between finite dimensional vector spaces can also be referred to as tensors. So I'm really bad at it saying a matrix or a tensor. So I'm going to try and clear this up right now. Matrices and tensors, they are different things. A tensor is a more generalized matrice. All right, so they are different things, but for this course, they are the exact same thing. So as you guys are going to see, I'm going to have a strain tensor, which is a 3 by 3 matrix, the exact same thing. And the only reason why is because we're dealing with the Euclidean vector space. Because we deal with the Euclidean vector space, these are going to be the exact same things. So everything that you guys know about matrices, you guys can apply those to these tensors. And we're going to look at that and the things that we can do with these matrices. All right, so let's look at the types of linear maps. This is where things may get a little bit confusing. So maps or functions between sets can be injective, which means each input has a unique output. These are going to sound really confusing, but I'm going to show you guys a little bit of pictures. Hopefully it'll make more sense. So the first one is injective. And I don't know why I put invective, but that should be injective. The second one is surjective, where every output has an input. The third one is bijective or invertible, which is both injective and surjective. So number 3 is just a combination of 1 and 2. And this is going to be the important one. And 4, none of the above. But again, what's important about this is we're looking at bijective or invertible maps. And you guys will see why later on. Now, Let's look at an example of what exactly these are. Let's say I have the function of f of x is equal to some scalar a multiplied by x. The first thing that we want to look for is it injective. So each input has a unique output. Well, in this case, this would be injective. The reason why is if I were to look at uh, an output, let's say I look at the output y is equal to 2. There is only one input of x that will give me that value. And when we deal with the example number 2, you guys will see exactly what this means. All right. So injective, it's very simple. What you want to do is you just want to draw a horizontal line through your function. If it intersects twice or more, so 2 or more times, then it's not injective because again, there can only be one output for each input. We look here, I see that I only have one output for each input. The second one is surjective, which means that every output has an input. So what you want to do if you're trying to determine if something is surjective is you want to look at the range of outputs. In this case, my range of outputs is that entire y-axis. Now, if I look at that entire y-axis, I have an output for every input. And again, this really sounds confusing, but the next example will help show it a lot more. But what I want to show you guys here is since this function is both injective and surjective, we say that this function is actually bijective, which means it's invertible. Now, when we're dealing with the finite element method, as you guys are going to see, a lot of this stuff is bijective. The reason why is think of this. If I have the strain in something, a strain tensor, I can find my stress tensor. But I can also go backwards. If I know my stress tensor, I can find my strain tensor. And that's the whole bijective thing. It's invertible. I can go from stress to strain, or I can go from strain to stress. Something like that. Now, it may seem confusing, so let's look at actual one where it's not. Let's look at the function f of x is equal to the absolute value of x. If I were to look at this here, I can see that there's actually two values of x that return me the same y. If I were to input 2 into this function here, I'm returned with 2. If I were to input negative 2, I'm returned with 2 yet again. So in this particular case, two different inputs gives me the exact same output. Therefore, this is not injective. All right, so two different inputs gave me the exact same output. That's what I mean by injective. The second one here is that surjective case. So remember, if something is surjective, then every output has an input. Now, if I were to look at this y-axis here, there's a whole negative region that doesn't have an input. For example, if I want the output negative 4, I can never get negative 4 because of this function. Therefore, there is an output, negative 4, which does not have an input. Therefore, in this case, the function is not surjective. So I'm just showing you guys what injective and surjective are, but in this particular course, we are going to deal with bijective maps, which basically means that they're invertible. All right? So with that being clear, the types of linear maps, let's talk about some of the properties we can do with linear maps. The first one, which is actually very important, is called the determinant. And now, you guys taking linear algebra, you guys know exactly what this determinant is. You guys probably know how to calculate it, but you guys may or may not know what it's going to be used for. As I showed you guys in our little course outline, I talked about isoparametric elements, which I said takes our elements that we defined in the previous lecture and makes the calculations much easier. The whole basis of those isoparametric elements is actually based on determinants, as you guys will see. So the determinant of a matrix is a real valued function that indicates the invertibility of a matrix as well as the change in area after a linear transformation. So that change in area part right there, that's what's going to be so important for us in the finite element method, the change in area. And it's going to be self-explanatory later on. So let's look at scenario 1 where we have a 2 by 2 matrix. It has components A1, A2, as well as B1, B2. The determinant of this matrix M, which we put as kind of the absolute bracket signs around the matrix, is simply going to be A1 multiplied by B2 minus A2 multiplied by B1. So it's actually very, very simple to calculate in 2D. 3D, well, it's a little bit harder. So if we were to look at a 3 by 3 matrix, it has A1, A2, A3, B1, B2, B3, C1, C2, C3. We can find the determinant, and the equation gets a little bit longer, but it's actually not too bad. Now, if we were to look at this and refer back to our triple scalar product, we can see that the determinant of this M here for 3 by 3 is actually equal to A dot B cross C. So this is one of the useful times that triple scalar product actually has some meaning, but other than that, it's not too bad. Now, if we were to go determinants of a 4 by 4 matrix, that's where things get a little bit crazy. Luckily for us, we're engineers. We don't worry about infinite dimensions. We're concerned about, say, something in 2D, something in 3D. Again, if you're designing a building, and I probably shouldn't use buildings because not all of you guys are civil. If you guys are designing a chemical plant or a furnace or something for 4 dimensions, well, then something's probably wrong with your design. All right. So one of the things that we're also talked about is it indicates invertibility. And that's important when we're dealing with these bijective maps. So how exactly does it determine invertibility? Well, it's very simple. If the determinant of a matrix M is equal to 0, the matrix is not invertible, which means that the rows are linearly dependent. Now, if the determinant does not equal 0, the matrix is invertible. So it's actually nice and simple. If it's equal to 0, not invertible. If it's not equal to 0, it is invertible. All right, nice and easy for these. Now let's talk about something else, eigenvalues and eigenvectors. And these things are always so sneaky. When I first learned them in linear algebra, I thought these are the most useless things I've ever seen. Then sometime in my undergraduate career, I say, oh, well, these are actually useful because they indicate things like column buckling. Now, as you guys are going to see in the finite element analysis, these are going to be one of the most important things, unfortunately. And you guys will see why a little bit later. So an eigenvector of a matrix M is a vector that, when transformed by M, retains the same direction. And the magnitude of the expansion or contraction of the vector after transformation is called the eigenvalue. So again, doesn't really mean a lot when you see words. It's better to see some pictures. So let's say that I have two vectors in E1, E2. I have a vector U and I have a vector V. And what I'm going to do is I'm going to transform these vectors using my linear map M, which goes from R2 to R2. Basically, I input a vector, I'm going to be outputted with a vector. So right now, after the transformation, I have kind of the faded ones, so those are the original vectors. Now, two scenarios are going to happen. The one is, let's say if I look at vector U, and I transform it by M. As we can see, the length or the norm of MU changed. Also, the direction changed. So therefore, this one right here, since there's a change in direction, this is not an eigenvalue or an eigenvector, nothing like that. However, if we look at vector V and we transform it by M, we see that this one actually maintains the exact same direction. Therefore, this is actually considered an eigenvector of M. Now, we also see here that the magnitude or the norm or the length of the vector, it shrunk, it contracted. And the magnitude of this contraction we say is lambda. So in this case, we say that V right here is an eigenvector, and that lambda right there is the eigenvalue associated with that eigenvector. All right, so this is the key here. They do not change direction after the transformation. Now, how do we calculate them? Well, let's start off with eigenvalues. So to determine the eigenvalues, which we say lambda of a matrix or tensor, we solve the following equation, where the determinant of m minus lambda I is equal to 0. Now we know what m is. We talked about the determinant. We say that lambda is the eigenvalue. So the only thing in this equation that might be unknown is I. So I right here is the identity matrix. So this is just going to be a diagonal row of 1s where everything else is equal to 0. You guys probably know what I is. So again, just like before, we basically have two scenarios that are practical. First one, 2 by 2 matrix, 2D. We have a matrix A1, A2, as well as B1 and B2. Well, if we were to go to our equation, the determinant of m minus lambda I, well, we see that this is the determinant of A1 minus lambda, A2, B1, and B2 minus lambda. Now we know how to take the determinant of this, so we get this equation here. And the key here is this equation is equal to 0. So therefore, if we were to look at the end here, we basically just have a quadratic equation. Therefore, we can solve for the eigenvalues. And if it's a quadratic equation, there's going to be two eigenvalues here. Now, we have a scenario 2, I guess, even though I put it as scenario 1, which is a 3 by 3 matrix. So we use the exact same formula to determine m minus lambda I. We get this nice determinant. And it actually gets pretty ugly. I'm not going to lie to you guys. This looks like complete garbage. Now, Even though it's complete garbage, we know that that garbage is equal to 0. Therefore, we have a cubic equation we can solve for lambda, so we can find 3 eigenvalues. And then this is where I give you guys my pitch on Mathematica, where I say you guys can do this by hand. You guys will have a lot of fun. Well, maybe not a lot of fun, but a little bit of fun doing this by hand. Or we can go into Mathematica, and I'll show you guys how to do this in Mathematica. Nice and simple, nice and easy. All right, so this is how we calculate eigenvalues. You guys are all really smart. You guys saying, Clayton, piece of cake. Now let's talk about the eigenvectors. So to determine the eigenvectors, which I'm going to call P, associated with the eigenvalue lambda of matrix M, we solve the following equation. MP is equal to lambda P. Now, if we look at this equation, we have a lambda in there. And remember, if it's a 2 by 2 matrix, we have 2 eigenvalues. If it's a 3 by 3 matrix, we have 3 eigenvalues. So if we're determining the eigenvectors, we're actually going to have to repeat this process 2 times if it's 2 by 2, or 3 times if it's 3 by 3. So we're going to have to solve this equation each time with each eigenvalue. All right? So let's say that we pick our eigenvalue lambda. Well, we have scenario 1, 2 by 2 matrix. Therefore, we have this possible thing where we just input everything from the equation, where we have A1, A2, and B1, B2, so that's our matrix M, multiplied by the vector P1, P2, so these are our eigenvalues. Those are unknown, is equal to lambda, which we know, that's our eigenvalue, multiplied by P1, P2, or the vector P1, P2. So if we were to look at this, we know what M is, we know what lambda is, we only have 2 unknowns, that's P1, P2. So if we expand this into the equations, we get 2 equations, and again, we have 2 unknowns. So on paper, this looks great, 2 equations, 2 unknowns. I'm an engineer, I can solve that, no big deal. Well, it's going to be a little bit tricky because there's actually infinite solutions. All right, because remember, an eigenvalue indicates a direction. It's not an actual just straight up vector. So there's infinite solutions to this particular case because it's linearly dependent. It's the same vector, the magnitude can just change. So what we do to solve this equation is we can assume a value of P1 or P2. Personally, I always say P2 is equal to 1, and then I can solve for P1. All right, nice and easy. So just assume a value, and then you guys can solve. Scenario 2, which again, I have a scenario 1, I don't know why, 3 by 3 matrix. All right, again, same thing. We utilize our equation above, and we can see that we have 3 unknowns, P1, P2, and P3. All right, so what we can do is we can make 3 equations, 3 unknowns. On paper, it looks good. However, just like before, there's going to be infinite solutions. Therefore, we're going to assume a value for P1, P2, or P3, and then solve it. So again, personally, I always pick the last one. So in this case, I'd pick P3. I'd set it equal to 1, and then solve for P1 and P2. Now, since there's infinite many eigenvectors, because again, it indicates a direction, what we typically do in engineering is we normalize it. So we find out what the eigenvector is, and then we normalize it so that everyone has the exact same answer. All right, so not too bad. Those are eigenvalues and eigenvectors, and as we're going to discuss near the end of this lecture here, they're actually quite important, especially when we're dealing with the results of our finite element analysis. All right, so next thing that we're going to discuss is invariance. So the invariance of a matrix M are values that remain constant after a change of basis. So remember, at the end of our last review, we said that we can change the basis and that'll change the components. However, there are certain aspects of a matrix that actually do not change after we do a change of basis. So we talked about a change of basis for a vector where u prime is equal to q times u. Well, we can actually change the basis of a matrix where we can say m prime is equal to q times m times the transpose of q. All right, it's going to be the exact same thing. And it's a little bit harder to visualize a transformation of m. So the best example, which we do in solid mechanics, is let's say that we have our stress tensor. All right, it gives us the stresses on each side of a 3D cube, and that is in relation to a particular coordinate system. What I can do is I can rotate my coordinate system, and if I rotate that coordinate system, the stresses on the cube are going to change. So if m is our stress tensor, and I want to rotate our basis by q, I can find the stresses in the alternate coordinate system. All right? However, when we're talking about invariance, these are things that do not change even after we rotate that basis. The first one, which is going to be very important, is called the trace, or invariant 1 of m. and it's simply the summation of all the diagonal components. So that first invariant is the sum of all the diagonal terms. When I write an equation out and I have a summation sign, I don't like writing it out because it does look confusing. Even though this is probably the most simplistic summation, it always looks bad when there's a summation. However, what I like to do is I'm just going to show you guys a picture. Let's say that we have a matrix M where it's A1, A2, A3, B1, B2, B3, etc. Well, the first invariant is simply just going to be the sum of those diagonal components. So for a 3 by 3 here, it's going to be A1 plus B2 plus C3. If this was 2D, it would just be A1 plus B2. All right, so the trace, it's actually a very simple invariant to calculate. And again, even after we change the coordinate system, this first invariant is going to remain the exact same. The second one, which is a little bit harder to comprehend, especially its purpose because it looks like complete garbage, is the second invariant. So the second invariant of M is going to be equal to 1/2 of the trace of M squared minus the trace of MM. So if we look at this, it's actually just a function of the first invariance of matrices M as well as MM. So if you guys look at this, it's actually not that hard to calculate, but the only mistake that students I've ever seen will do is they forget that it's the invariance of MM. They'll just go with the invariance of M. So keep in mind that we have an MM there. It's not a typo. Surprisingly, I usually am full of typos, but this one, surprisingly not a typo. If you guys are calculating the second invariant, it's MM. Now, the purpose of the second invariant is something that you guys probably won't see too much in this course. I'll introduce you to it, but it actually goes more into plasticity. So if you guys ever heard of J2 flow theory, that J2, that 2, second invariant. All right. But again, it's something we'll touch upon in plasticity, but we're not going to dive too deep into that because that is just a nightmare waiting to happen. The third invariant is, again, a little bit more complex computational wise, but it's something that you guys already know. The third invariant of a matrix is simply the determinant of that matrix. So we've already talked about how to calculate a determinant, but just know that that's also an invariant. So if I find the determinant of a matrix, and then I were to transform that matrix by a transformation matrix Q, well, the determinant of that matrix M prime is going to be the same as the original determinant. All right, so these are some of the operations that you guys can use. Very simple, very straightforward. Now we're going to talk about something important, which is orthogonal tensors. So again, in this particular course, when I say tensor, it's the same as a matrix. Tensor, matrix, interchangeable in this particular course. All right, so an orthogonal tensor Q is deemed orthogonal. So by definition, it is orthogonal if the transpose of Q multiplied by Q is equal to the identity matrix I. Now, as you guys are going to see in this particular course, where these orthogonal tensors come up are those transformation matrices. So if I want to rotate a matrix or rotate a coordinate system, that rotation matrix Q is going to be orthogonal. So due to the definition above, so again, the whole definition of an orthogonal tensor is the transpose of Q times Q is equal to I. We can also determine the following properties. 1, the determinant of Q is equal to plus or minus 1. All right, so if we deal with that rotation matrix that we discussed before, the determinant of that rotation matrix is actually going to be plus or minus 1. Now, this is also great because if we know that the determinant's going to be A, 1, or B, negative 1, we know that it's not going to be equal to 0, which means that that matrix is actually invertible. And this makes sense because if I were to take my stress tensor, all right, let's say my stress is in a matrix, and I were to rotate it to a different coordinate system. Well, what this means is I can actually rotate it back to the original coordinate system and nothing will change, which of course makes sense. Now, why do we say plus or minus 1? Well, this plus or minus actually means something. So if the determinant of Q is equal to plus 1, Q is associated with rotation. So if you guys were to go back to that tensor that we derived at the end of our last review lecture, we'll actually see that the determinant of that tensor is equal to 1. Now, if it's equal to negative 1, Q is associated with the reflection. And you guys won't see reflections that much. We're mainly worried about, or we deal with rotations. All right, so this is kind of the first major property. The determinant is equal to plus or minus 1. Now, the second one that you guys will see is the rows of Q are orthogonal. All right, what does this mean? Well, if I have my Q matrix and I have A1, A2, A3, B1, B2, B3, well, the dot product between those rows, they're all going to be equal to 0. This will come in handy when we deal with proofs, but other than that, it's actually rather forgettable. The third one is the columns of Q are also orthogonal. So in this case, if I have A1, A2, and A3 as a column, and B1, B2, B3 as a column, well then the dot product between all of those columns are actually going to be equal to 0. All right? And then the final one is the product of two orthogonal tensors is also orthogonal, not orthonormal. All right? Or I guess it's interchangeable, I guess, at this point. So that's going to be orthogonal tensors. And again, these are going to be the tensors that we deal with mainly when we're talking about the coordinate transformation matrix. When we deal with our stress matrices and our strain matrices, those won't be orthogonal. All right? You guys won't see those orthogonal. But if we want to rotate those stress and strain matrices into a different basis set, we do that using an orthogonal tensor Q. So that's where those are going to become important. What's going to be important for our stress and our strain matrices is going to be symmetric tensors. Now, in finite element analysis, I want to clear this up now. It will not always be symmetric. But for this particular course, it will be, which is great. As you guys are going to see, symmetric tensors are going to be your best friend. Now, some of you guys may say, well, Clayton, what is a symmetric tensor? You're hyping it up, but you're not telling me what it is. Well, a symmetric tensor S is deemed orthogonal, or I guess symmetric. So excuse the orthogonal there. I'll clear up all these typos, don't worry. If S, or tensor S, is equal to the transpose of S. What exactly does this mean? Well, it means that those off-diagonal components are the same. So Sij, or component Sij, is equal to component Sji. Now, as you guys are going to see, this is going to become your best friend because symmetric tensors are extremely common in engineering applications. Now, usually when we deal with engineering applications, things get more complex. But for symmetric tensors, it actually makes things easier. So it's one of the benefits of a symmetric tensor is it finally makes our life easier. And you say, Clayton, well, how exactly does it do that? Well, let's take a 3x3 matrix. So if I'm looking at the stress of a solid in 3 dimensions, the stress can be modeled as a 3x3 tensor, S11, S12, S13, etc., etc. We look at this, it has 9 components. However, if this is symmetric, so therefore Sij is equal to Sji, we go from 9 components down to 6 components. All right, so that actually makes our lives a lot easier. And once we start dealing with constitutive relationships, which is the relationship between stress and strain, this will actually make a very big difference. The fact that both our strain tensor as well as our stress tensor are symmetric tensors. So a little spoiler alert of what's to come. All right, so symmetric tensors also have some properties. For any two vectors u and v and a symmetric tensor S, SA dot B is equal to A dot SB. This is something you guys will see a lot in proofs, something that you guys don't need to worry about too much. All right, something that you do want to worry about or something that is of interest is this. The coordinate transformation of S, so S prime is equal to QS Q transpose, this is also going to be symmetric. All right, and then we have a third one here where an n by n symmetric tensor has n real eigenvalues associated with n orthonormal eigenvectors. So of course we can go n by n. However, for engineering purposes here, we are only dealing with either 2D or 3D. So if we have a 3x3 symmetric tensor like the ones above, we have 3 real eigenvalues with 3 orthonormal eigenvectors. All right. What exactly does this mean? Well, we're going to look at, I guess, property 1 and property 3, or property 2 and property 3 in the next slide for something called diagonalization. And this is going to be very important when we start talking about stresses and strains, not only from a solid mechanics point of view, but also from a finite element point of view. So, if a symmetric tensor S is transformed by a coordinate transformation matrix Q, consisting of the eigenvectors P, Q, and R of S, the resulting tensor is diagonal. Now, you guys look at those words and you say, I don't understand any of that. Okay, I'm an engineer. I'm not an English major. Don't give me any words. Give me something I can see. Well, I'm saying that if we have a symmetric tensor S, so we have S there, that has 6 components, and we have a coordinate transformation matrix that is special in that the rows of this coordinate transformation matrix Q are the eigenvectors of S. So if we look at row 1 of Q, it's P1, P2, and P3. So that's an eigenvector of S. We look at the second row, we have Q1, Q2, Q3. That's an eigenvector of S. what we find is that S prime, which is equal to QSQ transpose, is actually a diagonal matrix. So this means that the only non-zero components here are the diagonal ones. We're going to find that we have a diagonal matrix consisting of the eigenvectors, or sorry, eigenvalues of S. All right, so if we look here, we have diagonal components, lambda p, lambda q, lambda r. Those are going to be the eigenvalues of S prime, or of S. And the the off diagonal components, those are all actually equal to 0. So this is going to be important because when we do this diagonalization and we get those eigenvectors or eigenvalues as the diagonals, we refer to those as the principal values. Principal values. Now, if you guys have used finite element programs before and you guys are looking at the stresses or the strains in something, one of the options the program will give you is the principal strains and the principal stresses. What are those exactly? Well, those are going to be this matrix S prime. So what happens is if I have the stress on a cube, which is S11, S12, etc., etc., and I transform that by the eigenvalues of that, what it'll do is it'll give me this diagonal matrix, which will give me the principal stresses. All right, so we're going to talk about that a little bit more in the next lecture, but it's just something to be aware of because you guys will be seeing this slide again. Now, if we look at what we did above, we did a coordinate transformation. And remember that we said that we have something called invariants that do not change after a coordinate transformation. So if we look at S prime here, which is simply a diagonal matrix of lambda p, lambda q, lambda r, we can actually apply those 3 invariants, and those 3 invariants will also be the same for S. Now, since we're dealing with the principal values here, which are the eigenvalues, we call these ones the principal invariants. So I hope that makes sense, and with that, that is the end of our linear algebra review. And with that, that's also the end of this lecture. So do you guys have any questions concerning the linear algebra review or the course as a whole? As you guys will see, some of the lectures may end a little bit early, like today. Some of them might take the entire time. We'll have to wait and see. But as a whole, how are you guys feeling? Is there any questions, concerns?